So I welcome you to the first session on day 4, and then there will be tutorials. No, so today mostly the solar thermal cooling and heating content will be discussed, and I request all of you to be attentive, because this is very important topic in both in our countries as well as in Western countries. So now, Professor, you can
Okay.
start.
Yes, so we will continue on the tutorial of yesterday, and I had some explanation regarding especially this value. So if you remind me what we have seen in my day and one lecture, page 112, there was a small design of autonomous installation, and for the peak power of the global PV central, we said that it is equal to the energy needs divided by the performance ratio, the efficiency of the battery, and of conversion to the battery, and the mean solar radiation per month. Okay. So if we look, we are doing the reverse. We know the energy, we know the power peak. We a priori select a panel, okay? And this, we don't have to forget that it is for standards. So when we say that the peak power of PV panels is at 140, as we select, it is 140 watt per 1000 watt per square meter in standard condition. So it is a reason why when we multiply this power by the mean radiation, we selected 5 kilowatt hour per square meter per day, it is simplified with that, okay? So we will obtain some watt or some kilowatt, depending of what we said as a peak power. I am clear or no? Here, the energy produced by a PV panel, we said it is the peak power, and it is in watt, multiply by the EJP per day, okay? But this peak power is okay, in standard condition. So when we multiply this by this, there is a simplification of kilowatt. Okay. It is because there was a question, why is it we have forgotten. I was too tired yesterday evening to identify the thing. Is it clear like this? Okay. So it is the estimation of what is produced per day by one panel is this. Okay. The other thing where you are right, they made a mistake. I made the mistake here. So you're right, it is 70. So 70 panels. So it will change my data application, but I'm trusting you to give me the good value, okay? So après, we have to integrate 70 solar PV panels of Siemens branch 140 with 12 volt at the born of the PV panels. And now the next question was how much we put some PV panels in a string. So this is a string, we call that a string. How much in series and how much string in parallel. We have seen that it is advised that for the range of the power of our PV central, what is usually adopted, we are in this range, it is 48 volts in open circuit for the central. So the first is quite simple. How many here? How many solar PV collector in series? Four. Okay, because we said that we select this, so which has a peak power of 140 and an open circuit tension voltage of 12. So for sure, we have to put 4 PV panels. It's okay? Don't hesitate, because when you put in series, you add the voltage. Okay. Then I told you that a PV central has to be balanced. Okay. So we can't imagine to put 4 here, 4, 4, and 3. Okay. 4 will be a constant number for the string. So now if you said that I have 4 PV panels per string, if you divided 70 by 4, it should give you an idea of the number of parallel strings. So can you compute it, because I didn't do that?
17.5.
Sorry?
17.5. So you can take 18.
15?
18. 1 8.
Ah, 1/8. So if you do the calcul, you find that's it? Okay. So 70 divided by 4 is equal to 17.5, and it's right. You will select 18. Never below, but okay, up. So 18 string. So it is modifying a bit the global solar power peak of the centrals. Okay, can you give me the global power? So finally, it is how many PV modules? Seventy-two multiplied by 104. So you have 10 the power of your PV central is 10.08 kilowatt peak. Okay? Everybody is okay with that? Okay, so I'm good on this for sure. I'm bad on this. It is 18. Okay. You have also a rough idea of the inclination of the panels depending of the latitude. Okay, the inclination, the best inclination is obviously depending of the latitude. The more the latitude is high, the more the panels are going to the vertical. Okay, the more the latitude is low, the more the panels are going near the horizontal. Okay. A remark that I made yesterday, but it is very important. This kind of evaluation of inclination is made for a maximum generation of energy during the year. Okay? It seems to be obvious, but we can admit that in some cases we would like to have more production of energy during winter, where we need a lot of energy, than within summer, when we produce a lot of energy, but sometimes we don't need it. Okay. So this remark is that it is important for maximum of production of energy because it is an autonomous central. If it was on the grid connected, it could have been different. Okay. So thus, in our case, we will choose an inclination of 15 degrees. So it's not really inclined, okay? So this I will give you on the package also. Huh? So you just have to correct the right data, but this will be integrated. Okay, now sizing of the battery. So, I didn't remember if I told you to take a discharge. So we have several batteries, okay, that are available in place. So lead battery are the more common. There is also gel battery. So we have to put also 48 volts, okay, in a rack of the battery. So to connect the battery in order also to be consistent with the PV central and to have 48 volts. As I remind you, if I have two batteries in series, I take this one, 6 volt, 300 ampere hour. It's equivalent to a battery. So what are the characteristics of the equivalent battery? Yes, you had the voltage, so 12 volt and 300 ampere hour. Whereas in parallel, it will stay 6 volt and 600. Okay. So we will choose this one. Okay, because the other have too small voltage. We will have to put a lot, and the other could be less rare and not so mature. Okay, you can choose another one if you want, but we will select that. So they can be put together in series or parallels in order to at the end obtain 48 volts. Okay. Of course, the number of the battery is depending of the autonomy we want. Okay, at that time we didn't discuss about the autonomy, which is a key element, of course, for the battery. So what I suggest to you when I was introducing that is that you have to investigate local climate, okay, to see if it's a country where it is sunny every day, the rain is very rare, or if there's some period where you have no sun for several days and so on. First, investigate the local climate. Second, discuss with the customer. Okay, this is a school, donc a priori it's not operating the weekend, and so only 5 days, and maybe not in the period where there is bad weather or at the rivers where there is a very sunny river. Okay, so it has to be to know, to investigate local data. Okay, so today we don't know, we have not the possibility, but usually when you have a battery rack, you choose around 2 or 3 days of autonomy. Okay, but it could be more precise, discussing with the customers what is the use of the building, the period of the use of the building, and also local climate. If there's some specific climate, there is fog, for example, for 2 months in the year, it's delicate. Okay, so we'll choose 3 days. Okay, assumption. Okay. But in reality, you go deeply locally to understand what are the real needs. Okay, don't forget that. It has to be consistent with the use. Okay, so I decided that my battery have to be able to store 3 days of energy need. So around 145.86 kilowatt hour. So it is the same like for the PV panel. You have seen, you had them, you connect them in series, you had the voltage. So here it's easy to see that you will have 4 times this. That means 8 battery per string. And then after you complete to have your global autonomy. Okay, so we will connect 8 battery per string. to obtain a voltage of 48 volts. And then we identify the number of parallel string in order to reach our autonomy. Okay? So I leave you to think about that a bit. You see, the price of a battery is quite high. When you have a PV installation and you had some battery, it's increasing a lot because PV panels now are very inexpensive. All the other components are non-expensive. So it is the reason why that grid-connected PV installation and off-grid connected has nothing to compare in terms of price. Yes, the main price of this kind of installation in the battery.
While selecting the voltage, do we need to see the specification of the inverter?
Yes, the inverter has to be consistent with the inverter has to be consistent with the global power of the central, because the inverter helps to find the maximum power. Is tracking the maximum power, so it has to be consistent with the global power of the PV central. Also, the voltage has to be taken in consideration, but it is the maximum power that will help to design the inverter. Okay, so I said that number of battery is dependent of this autonomy. We select a depth of discharge of 80%. 80%, it is the maximum in your assumption. Huh? Remember, the more you are going deep in the extraction of energy in the battery, the less the battery lifetime will be. Okay, the shorter it is linked to the number of cycles and the depth of the discharge. So to be very comfortable and to have no problem in terms of maintenance, it's good to take 50%, but that means that you are doubling. If you just use half of the capacity, you are doubling the number of battery. So it's very expensive at the investment and less for the maintenance. So it depends also of the economic model you have. If you have a lot of money to invest, be comfortable and take a discharge of 50%. If you are just regarding the investment, you take 80% of use of the discharge, okay?
As per the plan, we have this equally. So that's how they have planned it now.
Yes, but I finished that and then I'm doing that. Yes?
I got a message that people are waiting there for this lecture.
But they don't follow all? They should follow all my lecture, no? No, I will. It will be in the second part. But I want to finish this. It will almost finish. Okay. So, yes, and if you take this value, you have to know that the lifetime will be shorter. So you have to plan to invest during the life of the central. Okay, so we said head battery must be connected in series. Okay. Like this, the total energy to be stored in the battery is just equal to this. If we consider, so this is when we consider that we are using all 100% of the battery. Huh? And if you consider only that you use 80% of the battery, you measure, okay, this. So thus, we need 127 battery. And so I will leave you check. If you find there is a problem, you will tell me and we will correct. Okay, but I'm almost sure about this. So the inverter, so I suggest one kind of inverter that is able to deal with 12 volt, 24 or 84 volt, and of course related to the power that we have in our PV central. So this, the name don't give you the data of the inverter, but if you look at this, I will give you there is the power, so the maximum power, which is really consistent with the peak power of the PV central. Okay.
So how that total equal is calculated?
Sorry.
30800 ampere hour. How that
Yes, it is the total of the storage capacity when we are connecting all the battery. Yes,
series and parallel, right?
yes. If we use 100%, but we don't use 100%, so we have to measure. We have to add 20% of this. This is equal to this plus 20% of this to measure, okay? Because we are using only 80%. Oh, this is to finish on the cost estimation, depending of the price that I gave before, okay? So you see, it's quite simple. If you have further question about the installation, you can write me, and it was to have a ROS design regarding PV, regarding the battery rack. In between there is the inverter. Inverter, the main thing is to be consistent with the maximum power of the PV central, so it is the peak power of the PV central. Remind that if the inverter is under design, so is not able to deal with the level of the peak power of your PV central, sometime when it is very sunny, very cool, the PV central could be close to its PV peak power, and the inverter, if it is under design, we will not be able to follow and to identify the peak power, okay? The maximum power, sorry. If it is the case, it is disconnecting the PV central. That means that all what is produced will not be used, okay? It is less sensible if the inverter is oversized. If it is oversized compared to the peak power of the PV central, you will lose some kilowatt hour because of accuracy. Okay, if it's too oversized, it will not be accurate enough to identify the maximum power. Okay, so you can lose. It could maybe be just a bit below, just a bit higher, or so, and below, not higher. So you can lose a bit of energy production, but it will never be disconnected to the application. Okay. But if he's not well sized and below the maximum peak power, you can lose a lot, because if he's disconnecting, he will disconnect until the power will become low enough to be able to track it. Okay. So it's better to oversize, but to be closest as possible. Is it clear how to design? So of course, after you have the tools. This is a rough design to just give an idea. Then after, when you have this data, you can go on a simulation tools that will give you a more specific and precise design. Okay, but at least you will not be far from that. But the tools will allow you in this particular place. Remember, if there is mask, if there is, you will have the real meteo file. So you can say, you can identify on 1 week how much you will produce in winter, on 1 week how much you will produce in summer. So, but it's just to have a good, a rough idea. Okay. Okay, so now we can start by what is planned today. So solar heating and cooling lecture. Keep no. Okay. Yes, it is so. Yes, PDF. Okay. So now we will go on the solar thermal side and see what we can do with this energy vector. Okay, so to remind you, there is two ways to big family of solar PV that we just deal with, and solar thermal. With solar thermal, it's a low density, so there is different technology, but it's going to low temperature. We can reach very high temperature. We have seen solar furnace, okay, but it depends on the technology. And if you want to reach higher temperature, you have to develop the surface or to concentrate and to concentrate the energy, and you can generate electricity. So to meet heating needs, you have heating and domestic hot water, so we'll see solar thermal. To meet cooling needs, there is direct solar PV coupling with heat pump. There is nothing special in the lecture that we will do. We will see how a solar thermal cooling system can replace a solar PV cooling system. Okay. And so we can make some cool through heat. And to meet energy needs, we have seen. So classically, on solar thermal, you have a reservoir and you can have a mirror or some specific adaptations that allow to increase the temperature. So the principle of a simple solar thermal collector is to have an absorber which is selective, very absorbing, At the back side, you have a fluid that could be air, water, oil, that is collecting this heat. And depending of what you put at the top of the absorber, you are losing more or less some heat, okay, or that allow to increase. Different technology of collector type. So more simple, it is unglassed plastic. So it's like wire, black wire, okay. You can do it in your garden or to have a hot shower. There is industrial unglassed absorbers that are used for swimming pool, for example, if you want to upgrade the temperature. The maximum operating temperature is limited, of course. Then you have glassed metal absorber with black coating, so what we call flat plate covered. You can reach around 60. Now there is 70 for water heating and air heating. It's good, and cooling, we will see. Glassed metal absorber, not cooling, sorry. A glassed metal absorber with selective surface. You can reach 90 degrees. So also for water heating and air heating. Then you erase the convective heat transfer when you have evacuate tube. So you can reach until 180 degrees. This it could be used for cooling, okay, with adsorption machine. Then you have non-tracking concentrator. So that means non-tracking. You remember about the concentrator. You have linear parabolic concentrators. That means the parabol are at least tracking on one axis, okay, and you have other kind of the dish. You remember the parabol with the Stirling engine at the focal, which can follow in two directions. Okay. So tracking concentration with 1 point focus, it is the dish, the parabol, and you can reach 1000, which is necessary to generate electricity with Stirling engine. Okay. Heliostat, so you can reach 100 and 500 degree, and it is classical heliostat if you remember a tower. Okay. If you remember the furnace of Odeyo, there is heliostats that are reflecting on a big parabol that are reflecting in 1 point, and here we are able to reach more than 4,000 degrees. Okay. But it's very rare. I think there's not too much kind of this application. So this is a large range that we can reach in terms of temperature, so that we can find some applications to many fields, preheating, heating, drying, cooling, generation of electricity. The problem of this technology is not the large range of temperature which is available. It's really nice to have such a large range of possibility. The problem is mainly the cost now, okay? Because it is made with, except the plastic, all need some copper, some mirror, so the price of such an element is higher than a classical PV panel. So even a classical flat plate collector with a glass absorber, selective absorber, heat exchanger, insulation, air tightness to be fully tight, it's more expensive than it seems to be a simple technology, very simple, but it's more expensive than PV because the price has decreased. So here you have some illustration. It is unglassed PV collector. We have seen solar wall, or it could be plastic also here on the facade. Classical flat plate covered collector and evacuate tube for the application of building. Here you have a nice illustration of very high unglassed unglassed solar thermal collector. Okay, you can see this black. It is made with stainless steel sheet all along the height of the tower in order to preheat the air or to heat the air of this tower, which is dwelling apartment. Okay, so this this principle, you have a porous solar steel stainless absorbing facade, and you are ventilating this air gap in order to the air to come all along the facade inside the building. So it's a very simple application. The more simple application. You can use it also for big space, industrial space, to warm, to preheat the air, or to dry also, because the level of temperature could be enough, could be sufficient. Collector with glass cover, so you have the absorber. The principle is to to transfer the heat that is collected at the level of absorber by a fluid. So there is many study working on the heat exchanger to increase the efficiency of heat exchanger, to increase the recovering of the heat. Also on fluid, there was also some fluid with nanoparticles in order to increase heat transfer. So many research from this. And also on materials, because as I told you, plate of copper now it's expensive. Okay, even if it is very thin. So to try to find alternative materials that are not so good as copper in terms of heat transfer, but are less expensive. So to find a compromise between the enhancements of heat transfer between fluid and the absorber and the quality of the materials of absorber. Okay. It's a big issue. Some nice integration in a house where you can see that there is also some effort to integrate this kind of connector in the envelope. So this is typically for domestic hot water. Or also there is some systems that allow to have domestic hot water and also heating system inside the house or the building by heating floor. Okay. It is very convenient with heating floor, because heating floor you don't need to have a high level of temperature. You have to be very low, maximum 27 degrees at the surface of the heating floor. So it's good if it's good adapted, but also very expensive. So evacuate tube is more delicate to integrate it well in the roof because of the shape. It is cylinder because they could mechanically resist to the fact that there is a vacuum inside. Okay, so if there is some rain or some thing, it will not explode due to this shape. So the principle that it depends, there is various we will see. Some are more, the more developed like this, with the absorber in the middle, okay, and the fluid circulation related to this absorber. You have also very simple evacuate tube where the absorber is it is a thin film, a black thin film, which is recovering the the inner surface of the internal tube. Okay, and so that means that there is water, full water in this tube. Okay, it's very simple.
This is a flat plate kind.
Yes,
Flat plate and then you have bolts.
yes.
Through heat transfer fluid.
Yes, for this, but there is also very simple that are which show in the picture like this, where the absorber is inside the tube, and so in the full tube is with water. So that means that when the sun shines and is absorbed by the internal tube, okay, that will hit the water. The density of the water will change, so like a thermosiphon phenomena, like we have seen with solar chimney. Okay, so all along here, the hot water will go up, and the cold water which is in the tank will go down. Okay, so there is a natural circulation which is made like this. I have tested such a collector even in a very cold climate. I put that in a freezer to see if there was no problem of frozen, because it is water. In such a design, the water which is in the tank and which is going in the collector is directly consumed. When you take a shower, it is the same water that is here that is going in your shower. Okay, so there is no alcohol, no. So the main problem could appear to be when there is very low temperature, but with very low temperature, it's incredible. There was this very interesting micro circulation phenomena, so it was very, very strong. So this is a more simplest technology. You plug in directly in the solar tank, vacuate tube, and inside the vacuate tube there is the absorber. It's a thin layer of absorption, and the water is going inside. And the one with this kind of technology, which is more efficient in terms of heat exchange. So this absorber with the circulation is this kind of tube that you have presented in your lecture, where here you have you are plugging to the heat exchanger with that brings the heat to the tank. So it's more sophisticated, more efficient, of course. But more expensive than this, which is very simple technology. Okay, so very interesting and of course more efficient. Thanks to that, you can reach 180 degrees, not with this system, which is more dedicated for domestic hot water, so you will not reach so high level of temperature. But very economic, not expensive. Okay, so what is important also, it is the positioning of this captor, the inclination, the optimum inclination. So it depends of your system. If it is only dedicated to domestic hot water, it's okay. There is no real challenge for the optimum inclination. If your solar thermal is also for another application, solar cooling, for example, or solar heating in the flow injection, solar heating, it will be very important during winter time. So you have to focus on the winter, okay? So the winter, I remind you, the sun is lower in the sky. So the inclination will be higher. If for system, yes, is for heating, yes, it will be more close than 60 degrees than 30 degrees. If it is for solar cooling, it will be more close from 30 degrees because we want to produce maximum during summertime to cool. Okay, so it's the same kind of preoccupation. What is interesting is depending, do you want to produce the maximum all the time in the year or at a specific period? And so if it is at a specific period for a specific need, you have to focus on the position of the sun in this period. Is it high? Is it low? And also the number of hours of sun per day and so on and so on. Okay. Never forget the final need. Okay. So the efficiency depends on the technology. I said, should we have a collector with copper, with very selective coating, ambient condition, so it's very important. If you have a flat plate collector without cover, that means without glass cover, the wind is very, 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 very important. If there is wind, all what you expect to collect will go with the wind. Even if it's a solar flat plate collector with glass cover, it could be, when there is a lot of wind, could have impact on the efficiency of the solar thermal. The sky temperature, obviously, because your solar collector, it has higher level of temperature, so is emitting with the sky, okay? So it's more delicate, and it's not good for solar thermal to emit. It's good for solar PV to emit radiation to the Celeste volt. It allows it to cool down. It's not good for solar thermal. That means that you are losing some heat. And there is, yes, very important, flow rate, inlet temperature, ambient temperature are parameters that are very important for the efficiency. Some example of absorber. So this is the one that we have developed, you remember yesterday when I was presenting PVT with a fractal heat exchanger. This is the heat exchanger, okay? So it is an aluminum. So you see the heat exchanger, you have different with other kind of aluminum, composite with between aluminum and copper, and even Dualson has made a polymer heat exchanger. Polymer is not very famous for heat conduction, but it's famous for the price. So this polymer was including some particles of metals in order to enhance heat transfer. And the originality is that the price is very low because you can produce it very fastly. And this is a kind of exchanger with copper. Okay, so a lot of evolution on the absorber due to the price of the metal and trying to keep a good heat transfer.
For polymer, I think thermal conductivity will be lower.
Yeah, yes, for sure. So they add some particles of metals in order to increase the conductivity of the polymer. This is manufactured as a roll bond. It is a roll bond technology. It is a heat exchanger, the kind of heat exchanger, not the shape, but the kind of heat exchanger that we find in a fridge. In the fridge, inside the wall of the fridge, you have aluminum heat exchanger that have particular shape for the fridge that are made with the same technology. So this technology is called roll bond. Roll bond. So you have two piece of aluminum two foil of aluminium. In one, you are drawing with ink the draw you want. You can have an ink exchanger with your face because you can. It's just printed on one foil of aluminium. Then you put the two foil of aluminium. You hit. Okay, when you hit, there is a melt. It's a connection of aluminium, the two foil, except in place where there is the ink. Okay. There is no mixing where there is ink. So then after you open at the border here where the two foil and you inject air, compressed air. And where there was a ink, it's I don't remember the name in English, but it's okay. And where there was no ink, it stay joint. Okay, so with this technology, it's very funny. You can and efficient. You can draw the heat exchanger you want. Okay, it is called roll band. So they explained that we were able to have such heat exchanger.
You're doing the purpose of 3D printing.
Yes.
By blowing air.
Yeah, yes, you can. And now, yes, you have 3D printing that can do it. Okay, so regarding a flat plate collector, when we receive 100%, okay, we said 100% of solar radiation, there is 8% which is reflected, usually. Okay, then after you have 15% which is lost here because there is air and there is convectivity transfer. So between absorber, okay, convection and the glass and out. You have 88% which is emitted outside, okay, by the absorber. Absorber is emitting in infrared. So the glass, which is opaque to infrared, will allow to keep the radiation inside, okay? But there is a bit loss of radiation infrared. You have also, as you are heating, some thermal loss at the backside of the collector. That is the reason why you have a big layer of insulation in order to avoid heat transfer between the heat exchanger and the backside. Okay, usually, so you recover around 60 to 70% of the incident radiation, depending on the quality of the flat plate. If you have a vacuate tube, it's higher, of course. You are neutralizing the convective loss. Okay. So you have to have big absorption coefficient and low emissivity. It's good. So very selective absorber. Absorber with high conductivity, if possible. The best is the copper, but the more expensive is the copper. So there is a lot of research to change with keeping the same conductivity and okay, and the roll bond process, I discussed about that. Good thermal contact is important between tubes and absorber, and air and water tightness, it's essential. If you have a leak of air in your collector, that means that you will have humidity that can come in. Sometimes you see that when a solar thermal flat plate collector is bad or is old, there is very often air inlet that appear, and then with humidity, and sometimes you will see some condensation. So you can imagine if you have water condensation on this glass, you lose a lot of energy. because water is also opaque to infrared. So infrared coming from could be stopped. Okay. Classical data about this. So when it is a classical representation, sorry, I've got a better, but just to show you the three things. So it's a classical curve of efficiency of a solar thermal. Okay. And this is the difference of temperature between the solar collector and the ambient temperature. And this is the efficiency. Okay. In this this point particular is called optical efficiency. Okay, it's the optical quality of your solar collector. The higher it is, the best it is. Those we call that this range to 100% of efficiency. This gap is what we call optical loss. Okay, this is 100% of efficiency. So the gap with this between this point and 100 is optical loss. Okay. Then when you are going below, it's not due to optic. So the absorptivity, the glass cover, and so on. It is linked to the thermal loss. Okay. So of course, if you reduce this, the efficiency will be better at higher temperature. The classical formula of the efficiency, it's okay, you have seen so this part between this point and 100% optical loss, this part is thermal loss, due to thermal loss. The classical expression is like this, so a coefficient minus what is representing the thermal loss, so the mean temperature, depending on the mean temperature of the solar collector, of the water in the solar collector, and the ambient temperature. Okay, the thermal loss is linked to the difference of temperature between inside and outside. Okay. So multiply by this equivalent conduction coefficient, sorry, and divided by the radiation. To be more accurate, the real one is like this. It's not a line, but it could be a bit curved. So some manufacturers of solar thermal are giving these two coefficients. You have one coefficient here, one coefficient here due to thermal loss, and this one is the same, it's optical loss. Optical efficiency, sorry. Okay. So yeah, it's better. So you have better idea, but I wanted to show optical loss. So okay, unglassed, there is almost not optical loss because there is no glass. So if no glass, no problem. Okay, there's no reflection on the glass, and but you can see that the efficiency decrease very fastly. So it's good for not high level of temperature. Then here you have glassed black absorber. So you see it's not really linear. Very often we put linear, but it's a bit curved. Here it's glassed with selective absorber, and here it is evacuate tube. So the main characteristic of the different technology. Evacuate tube, you have more optical loss because, have you seen, you have a double glass because we need to generate vacuum. So the loss due to the glass is a bit higher than for the other. But could allow to maintain a good efficiency with increase of temperature. Okay? Yes? Yes. Globally, yes, there is less thermal loss, yes.
So is it like that, in spite of the fact that temperature is high,
Mm.
in my tube temperature is very high, and outside it is like ambient temperature.
Yes.
So
Yes,
it
thermal
is-
loss is indoor compared to outdoor, so the delta T, okay? So mean temperature of the collector compared to ambient temperature, and it's right. Here, the thermal loss are very negligible
okay, so that's because of the
because
vacuum
you
tubes.
erase the convection.
Yes.
Because here in the thermal loss, you see convection phenomena because you have air,
Yes.
so it's hot here, and so you have a circulation of the hot air inside that exchange with this glass and generate thermal loss.
And I have one question regarding the efficiency here in previous slide. So can we find some threshold kind of solar radiation by using this formula? Because if the second term minus term is equal to eta naught,
Yes,
then efficiency will be 0.
yes,
So that means there is a threshold intensity, solar radiation. Below that, our system will not operate. So it should be more than that. By seeing this formula, so
yes.
am I right, or there is a misconception?
No, it can operate with small g. G is a global radiation.
Okay. So
Yes.
if G is lesser than this value, let us say I have some value of UL, operating temperature, and ambient temperature. By mathematically, if you are fitting that, let us say this minus quantity is equal to eta naught,
Yes.
then corresponding to that, whatever G we will calculate,
Yes, but
below that,
you have we have to notice when G is low,
yeah.
T will be low, will be close for ambient temperature.
Hmm.
Because the both are changing.
Okay.
We will not have a high mid temperature
Yes.
with a G low.
Low.
Okay. So these are moving together, very dependent. Okay. So yes, I agree with what you said, but when G decrease, T decrease fastly also. T
Yes.
min will decrease fastly.
Mm.
Okay. And when there is no G, there is ambient temperature in the
Yes.
solar collector. Okay.
Okay. Thank you.
Yes. Good question, but yes, T mean temperature and G are very, very related. Okay, some example here. I found some different technology. The bad thing is that around that, some industry have disappeared already due to the fact that PV is now very inexpensive. It's a paradox. PV was very expensive due to when you look at the PV panel, the technology which is implied is higher than in solar thermal. Solar thermal is quite simple, but the materials that are used are more expensive, and with this range of solar collector, you can just do heat, can just generate it. So yes, and it's better to sell electricity than to use your own heat. In terms, the main problem is the business behind. It's not the need, the answer to the need, because you are able to answer to a lot of needs with solar thermal. But in terms of business, It's better to produce electricity even if you sell it, you don't use it, okay? So, but it is some some example and some coefficient, so you can see, you can directly see which which collector has a very good optical 082 compared to the other. This one is very well, okay? And you have also, so this one is very good in terms of probably insulation, which is behind the heat exchanger. This not so good. So it gives you straight an idea of the optical and the quality of the heat loss. Just seeing these two parameters, okay? Okay, the test for a solar thermal collector are following standards. So, of course, the efficiency is depending of the radiation and of the external condition, so ambient temperature, wind. So the standards, you have to test it under 1 meter per second of velocity, temperature, and the inlet temperature. So the standards are, when you test the solar thermal, you will start by inlet temperature, then you will change the inlet temperature to see how it behaves, and it allows you to determine the curve as we have seen at different temperature, inlet temperature, okay? One important thing, as pity that I can't write. In this kind of bench, it is artificial light, okay, that generate artificial solar. It's not really important the quality of the light, because compared to a PV, it's very important, because PV the conversion around one wavelength, whereas solar thermal is taking everything, okay? But there's one important thing that sometimes people that are testing solar thermal are making mistake. Your solar thermal collector is heated, and it is very important to consider that it can emit infrared near the sky, in the direction of the sky, the celeste volt. Okay? It's very important, because if you don't consider that it is emitted also in direction of the sky, you will overestimate, by this test, you will overestimate their efficiency. So how can we simulate here that this collector is emitted in direction of the celeste volt? You don't see it, but this frame here is for a big glass, which is over. We can see here some reflection. There is the light here. There is big glass here, and there is the solar collector under. Okay, and it is a double glass. It is a double glass inside which there is cool air. Cool air is circulating in this double glass. Cool around 5 to 6 degrees. So there is a cold glass, finally, that simulates the celeste volt. Okay? So you have radiation, okay, coming from the artificial light, absorbed by the solar collector and so on, and the solar collector is emitted in direction of a cool surface, which is this glass, inside which there is a cool airflow. It is the condition to have a quite accurate evaluation of the efficiency of solar thermal collector in control condition. If you don't do that, you will overestimate the efficiency because the emission of the solar thermal in direction of the CLS volt will not be taken into account. So you are neutralizing a part of the loss. This, okay, which is 8%. So it was just, but important when you test in a control condition, solar thermal. Okay, so some kind of integration of solar thermal. So you can see this is not integrated. It's the same as PV, huh? Not really integrated, but not so bad, and fully integrated here. Here also you can find like PV, some rack like this in the flat plate roof. Of course you have to be careful of the shadow. It's less delicate than PV. Hein? The shadow effect is less delicate. It is not because you have a small shadow here that it will destroy all your efficiency of the solar. That means you will just receive less radiation, but it's less delicate. But of course, you have to be cautious when you are positioning these two, not to have cell shadow. Here, it's also integration in a balcony. Could be also now vertical. You can see evacuate tube on the balcony. At a bigger scale, the leader, the big scale solar thermal production for coupling on the grid, solar thermal grid, solar thermal distribution is Denmark. They have developed a lot solar thermal and injection on the grid. So here, it's not a PV central, it is a solar thermal central connected to the thermal grid of a city. So you can see you have 8,000 square meters of thermal collectors that are providing 15% of the heating and domestic hot water need of 1,000 homes.
All are evacuated tubes?
Hmm?
These all are evacuated to flat?
Evacuate tube. And in this way, of course, maintenance and things like that. So yes, Denmark is one of the leaders on this. Okay, so for application space heating, yes, I already said that. Underflow heating, pool heating. Now pool heating, especially in Europe where it is cold during winter, most of the municipal pools are heated and they use solar thermal. So it's one of the good application of this. For the solar thermal for domestic, for example, there is one constraint, which is what we call stagnation temperature. It is also a problem with solar thermal. Is it when you don't use it, it's coming hot, 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 hot. You have to evacuate at a certain stage, or you can see some people put some screen on the solar thermal. So because when you are going in a travel or in holidays, the family don't use anymore hot water, and at a certain stage it's becoming too hot, okay? Because it's a closed loop. So there is a system that allow to avoid that. More simple is to have a screen on your solar thermal. The other is there was a drain back system, so you are comment on dit, you are empty all the hydraulic system and store the heat transfer fluid in a tank, okay, and don't use the solar thermal. And then when you are coming again, you are filling all your loop and use it again. You have also, in terms of maintenance, to change the fluid every 5 years in Europe, because in Europe the fluid is water plus alcohol, okay, in order to avoid to freeze during winter time. So, and this fluid aging because heat and cold, and it's better to, it's suggested to change it every 5 years. Okay. So there is facing that there is constraint that is not in the PV in terms of maintenance. If also you have a leak of water, because it's tube everywhere, it's delicate for the maintenance. So this is in a very big competition with PV, a PV coupled with heat pump now. For this, because of maintenance, because of the price of the materials that are required, and also to install it needs also a kind of expertise. Which show you there was a lot of problem on such installation in France in terms of energy consumption. I will explain you later why. Okay, some example in Grenoble near Savoie. So it's well developed solar thermal for social apartment, because it's allowed to decrease the charge of the people that are inside if you can heat like this. So it's a nice installation of solar thermal for social apartment. And there is still a support from the National Agency of Energy and Environment to push for that, but to push more now a big scale in order to develop heating grid, central heating grid. ADEME is pushing a lot to have a centralized production of heat distributed in buildings, and so it is well supported. You can couple this also with heat pump like PV, but so heat pump in order to increase the efficiency of the heat pump, the global efficiency of the system. So it could be an uncovered solar thermal collector. You just have to upgrade a bit the temperature, and it's quite well. There was also some attempt about that. This is application where you are generating heat for a domestic tank, domestic hot water tank, and also heating system. So heating system on the floor. Okay, it has been well developed in France for heating system. It's quite comfortable. Heating floor is quite comfortable, and the application is also well adapted to that. So this is a classical installation for both domestic hot water and heating of a house. I don't know at what time we have a break. Now? Okay. So yes, it's interesting if you have a break now, because this second part is for cooling. Okay. And this special application for this afternoon, the second cooling. So we can make a break now.